Okay, a couple of reflections from last week. I can see that the lab assignments or the lab reports are rolling in, so that's good. For some reason, and that's not the first time, I can see that some people have troubles uploading some files. The submission box is wide open, so there's no limit on the files you can well, you can submit. Well, try not to submit 100 files, but you should be able to just keep submitting. The only thing is that there could be a size cap on that. So if some of your images are not up to par as far as the size of it, like they're too big, it might give you some trouble. Well, that's why I suggest the Photoshop, and you should be able to have access. You should have access to that Photoshop as our college students. You should be able to download it onto your computer and use it. If not, there are those computer labs at school. You're welcome to use it. If you have some troubles getting those onto the Adobe Cloud, if you have troubles downloading onto your computer, just call the IT department, right? They will walk you right through it. Or you can just take your laptop to them and they'll put it on for you. All right. If now there's a kind of a cool way of getting around it. There is that thing that's called a snipping tool. It looks like this. You can just go and just type snip, and it's going to give you the snipping tool, and you can fire this thing up. So here's how it works. You can just select that, and you can highlight whatever part of the picture that you have, and you can go file and save as whatever you want. You can name it, and that is going to produce a file that is not as huge as sometimes you have it straight from your cell phones. All right. Where is that? I'm just going to close that. Save it. No, we don't want to save it. Okay. So that's a bit of a trick here that you can use. It wasn't hard just to Google find your free student software. Yeah, so but then again, the IT department, they're there to help, and I'll tell you, comparing to other institutions that I had the pleasure to work with, our IT department is actually pretty good. They are very helpful. All right, they will, yeah. So that's what I have to say about them. They are pretty nice people, right? And I'm not just saying that. I experienced that. Okay, so a little reflection on the lab reports. I'm going to give you some suggestions once in a while. It's a common practice, and I'll give you the example here. What do they write here? Things like zip ties, screws, tape, electrical tape, or other small things. When it comes to listing the materials that you're using in the work order, well, it's not very practical to list every single screw, every single nut, every single zip tie, every single whatever. So quite often it's a common practice to include that as miscellaneous materials, and you just list that miscellaneous materials, and quite often many companies charge a flat rate. So could be $10, could be $200, depending on the size of the job, right? I remember when long time ago, I used to do the electronic bench at one of the music stores. It used to be called Music Mart. It doesn't exist anymore. But years ago it did. It was a pretty cool store, and I was the dude downstairs fixing the keyboards, amplifiers, and whatnot. And with every repair job, that was early 90s, in the bill for the client, I was listing miscellaneous materials, and we would charge $5 flat. So that would include the solder that we have used. That would include anything else that we had to pretty much resupply some of the expendable materials, right? So that's the thing. Now, the other thing I noticed that some of us are listing the tools that you're using in the materials list. Well, it's a school, so I would expect that to see that. So I'm going to address that. When it comes to list of the materials, when you're putting this thing on a work order, well, the work order is our lab report. All right. So when you're listing that, don't list things like side cutters or rulers or tools that you're using, screwdrivers and such. This is for the materials that you will be billing or the client will be billed for. So you can list, I just give you some example of what would you list as here. Like for example, one, right? So there's the quantity, 70 volt speaker station, and you can put a model number there. You can put 300 feet, 18-2 stranded cable, and then you can, in brackets, you can put whatever you're charging per foot, or not necessarily, but you can. All right, now here's the thing. I said lot, all right, miscellaneous materials, $ flat rate. Lot is a term that's being used to specify an unspecified amount of something, right? So you're not going to say 17 screws, 32 washers, and so on, so on, so on. Lot. It's just some unspecified amount that would just take too long to count all that little things. So it's a common word to use. So it's a lot, miscellaneous materials, flat rate, right? You can use that. Then 70 volt volume control, you can put a model number, 1 single gang utility box, 1 EMT conduit, and usually if it's inside the wall, it could be 6 feet long or so, whatever, right? Then 1 EMT box connector. So that's what we have used in our lab. So you can present things in this way, right? So notice that I'm not listing any tools like a magic marker or a permanent marker or electrical tape if I'm using it, or any kind of mounting screws and things like that. That would be in the miscellaneous materials, right? But well, actually, yeah. So the miscellaneous, but tools such as side cutters, pliers, screwdrivers, and things like that. We're not listing that as the billable materials. We might notice that those things being listed in some of the other subjects, or my subject as well, lab paperwork, just to describe the tools that we will need for that. But that has nothing to do with the billable materials as far as work order is concerned. Right? So that as far as the reflections. Now let's take a quick look at where we are standing right now in our course. I'm just going to call up the content here. And if you look at the course outline right here, that's where the course plan lives. And that's the second file from the top, right? This one right here. I'm going to zoom in a little bit. I do that. Yes. Hopefully you can see some of that stuff. So here is, will I go down, down, down? Here is the theory schedule, all right? And we are during week 4 right now, January 24, 28. So we will talk about the coaxial cable and signal routing and multiplexing. And next week, I'm going to deploy a test, and the test is, for the people who haven't been in my class yet, it's going to be just as it was in the tools and safety previous term, which is online. You're going to have, I'm going to give you a week to do that. It's an open book test. The questions are designed that you have to look for the information in the lecture post-it notes, or posted lecture notes, as well as some of the notes that you made during the live online classes, plus they are being posted on YouTube, so you can go back and review some of the information. The idea is that I designed those questions in such a way that you have to look for the information. If you don't remember most of it, you should be able to. But then here, there's a lot of it. So some of the details you might have to look for in the posted materials and the videos that are posted as well. Then the idea is that basically while you are doing that, and I designed the questions in such a way that even while you're doing the test, you are still learning. You are retaining the information and make it a little bit more permanent in your brains. Okay. All right. So section 3, no. Okay, so there's a question. So section 3 does not have a lab tomorrow. Yes, section 3 has, all the sections have labs this week, except it's not the A groups, it's the B subsections. All right, so last week, all the sections 1, 2, 3, 5, 6, we had the labs, but it will be just the A part of the, so if you're in subsection A, you would be attending the lab last week. If you're subsection B, again, section 1, 2, 3, 5, 6, just the B people with the B subsections attend the lab. All right. Now, there were some people that last week, there will be people from section B that joined the section A's. So I let them stay. We let them stay. There was one case that the class was full, so I was just sorry I wasn't able to let you stay in because all the stations were filled up. So if you were in section B and you attended the lab last week, then of course you're not going to have to come this week. So, but it was just one of those things. From now on, please follow your schedule. When you're scheduled for the A sections, please join the labs during your scheduled times. Section B, subsection B, please join the class during your scheduled times. We only have CDL 1010 is a bi-weekly class. Yeah, well, I can't speak for any other courses. All right. Whatever, our course is set up in such a way that it is set up and it has a life of its own. Other subjects are to be taken up with the professors and instructors that have to do with those other subjects. Okay. All right. So now the other thing is, yes, I'm recording this session, but this session I'm not going to be posting. I will be posting last year video that I made when it comes to the coaxial cable and things that have to do with that. It's a little bit longer video, but again available for you to review as you please. And basically it's the same thing now. Today is the same thing as the other video, so we're repeating that from last year. Of course, it's the same course that last year. Now today we have sections 1, 3, and 5. Tomorrow's I think it's tomorrow scheduled. There's going to be a theory there's going to be the repeat of what is today, but it's going to be for sections 2, 4, and 6. Right? Of course, anyone, because it's online, you can join as you please. You can cross-section join the classes, right? But there's going to be only one video that's posted, and it's the one from last year. Unless there is something important, everything is important. Unless there's something that I feel that I missed last year and I added this year, then I'm going to add it as kind of a supplement video. All right, enough talk. Let's get to our topic here. So this presentation, you have it already available for you to download from the content under the student items, and you can follow that, and you can save it, download, save it. You can even print it and keep it in your notes. Whatever makes you easy, what makes it easier for you to learn. All All right, so it's a little, it's a longer lecture, so it's split into 2 lectures. So we have 4 sessions, 2 sessions for section A and 2 sessions for section B. So today we're going to take on half of that, and the other half we'll tackle whenever it's scheduled later on this week. All right, so when it comes to links in telecommunications, remember, what do we distinguish as links? It could be copper, could be fiber, or it could be air. Right? So copper is considered as electrical wires that can carry electrical signals, and the copper cabling has, well, they take different forms based on the purpose that they serve. So they can be built in order to serve the purpose the best they can for the type of signal that they have to carry. Right? Now, coaxial cable, right? Also sometimes called a concentric cable. What is it that it makes it coaxial or concentric? It's pretty much the same thing. You can see that there are 2 conductors. One is the outside conductor, right here, and through the connector inside, it is connected to the outside, something that's called a shield. And it actually serves as part of the conductor inside the cable. And also it has a core, copper core, that goes inside. So the cable has 2 conductors. The outside conductor, right here, it's connected through the connector and inside the cable. It's an outside conductor. And it also has an inside copper core conductor. And those 2 are separated by that's called a dielectric. Dielectric is another way of saying an insulator. Right? Now, because they share the same axes, right? They're on the same axes, so there's one here and the other one is around it. Well, that's what makes it concentric cable or coaxial cable, because they share the same axes. Right? All right, so this is how it looks like inside. This is just the graphics of this. Somebody used Photoshop, or maybe somebody used some other modeling software. That's the idea of it. So here is the metallic shield. Okay, it goes all the way to the other end, and it has a dielectric insulator, or insulating insulator, right? And it has a center core. Now, this is what it looks like if you're looking straight into it, right? It has the outside metallic shield, has a dielectric that separates these 2 conductors, and it has the center core. The dielectric materials, well, it's usually like a PVC material right now, but some of the bigger ones, they use air. Some of the thick ones, they could be 3-4 inches thick cable. So they just have plastic separators that make sure that those 2 conductors don't touch, and the dielectric is as air. All right. Now, in reality, it looks like this right here. The top right picture here. Here's the braided shield, foil shield. Sometimes it's a double shielded. So here has a foil shield and a braided shield. Okay. It also serves as a conductor. And then here is a center conductor, and here's the dielectric, and of course it's wrapped up in the outer jacket. Okay. So what they write here? A 2-conductor cylindrical transmission line, typically comprised of a center conductor, an insulating dielectric material, and an outer conductor shield. This type of a cable was invented during the Second World War times. That's when the radar was being implemented. That was the beginning of the implementation of radar technology. And the purpose of that cable was to serve as a radio guide. Okay, radio guide. So then, because of the radio guide designation, those cables are called they have designations of RG, stands for radio guide. The purpose of that was to deliver radio waves from the transmitter and receiver that was on the bottom of, well, it was on the ground level, and the cable was used to communicate with the antenna or the radar that was on the mast. So the signals that were going back and forth were basically radio waves. So the cable served as a radio guide. How can you transmit radio waves back and forth? Radio waves you can transmit through the air. The best example is your car radio. Right? The car radio receives the waves from the transmitter that is somewhere in the city through the air. Right? But if you want, you can also transmit the radio waves through a cable. So some of the radio guide or RG cables are being used as transmitters. Now the radio guide also is used, or the RG cables are also used to transmit cable television, or the television signal, not as much as they used to, because now things are turning towards the internet. Very rarely you're going to see the cable TV in an analog form. However, sometimes, maybe in some part of the world still. Also, these type of cables are being used to deliver the internet signal to homes. So you can, well, right now, what are the types of signal that you get as an internet? You can get it through the optical fiber, which is the best, because the bandwidth is just the biggest bandwidth, or the widest bandwidth. What's a bandwidth? It's the amount of frequencies that you can transmit. It's just how much signal you can pack into that cable, and the cable is going to handle that, right? So optical fiber or fiber optics is the best right now when it comes to that. Then you can have the cable, the internet through the cable, and what it means through the cable is the coaxial cable, the concentric cable, this RG, and then here it is. Usually to your home or to your business, if it's a cable, internet through a cable, it's going to be RG6, and we'll talk about what these are. There are the different designations: RG, radio guide, RG6, RG11, RG58, RG59 would be the most commonly used types as far as the consumer and most of the commercial uses, right? Now there could be some special other radio guide types that would be out of this spectrum, but it will be they will have different designations that would be used to deliver the radio signal from the transmitter to the big antenna. Right? Now, also I'm going to mention is that when it comes to delivering the internet signal to the building from the outside, the internet is in an analog form. The internet signal, it's in an analog form. It's like a radio waves, right? Then in the modem, that signal hits the modem. That is basically the first thing it sees when it comes to your home or a business, commercial. It's the modem. What does the modem stands for? It's modulating and demodulating. Modulating, demodulating, modem. All right. So the modem modulates the signal toward, like, if you're transmitting the signal, if you're uploading, which means you're sending the signal from your home towards the internet, towards the cloud, that device is going to modulate the signal onto an analog form. Right? If the signal is coming, whatever is coming towards you from the World Wide Web, and it's hitting your house, for you to receive that signal, that modem is demodulating the signal. So it's constantly modulating and demodulating. Right? So the internet signal from the modem towards the cloud, which is the World Wide Web, right? It's in an analog form. And the signal from the modem towards the rest of your building, could be a house or a business, is in the form of a digital signal. Okay? So those cables are being used, and we'll talk about these, and we'll talk about certain characteristics that are involved when it comes to these type of cables. All right, now just zoom this thing in a little bit so you can see it better. So you can see it better. Remember the Red Riding Hood story? Grandma, why do you have such big eyes? Because I just saw the gas prices. All right. All right, so what did I write here? A series of standard types of coaxial cable were specified for military uses in the form of RG, and there's a designation number. Right? Also, you're going to see something that's called RG, which stands for radio guide, and then there's a designation number and slash with a U. What does the U stand for? It stands for ultraviolet. All right, ultraviolet resistant. Which means you can install that cable without any other protection on the outside of the building, and it's going, if it gets hit by the sun, ultraviolet rays, it's not going to get damaged. If it doesn't have that U designation at the end, within a year, that cable is going to disintegrate so badly that it's going to look like a hardened sponge, and if you can just crush it with your hand. That's how bad those UV. So basically, the U stands for UV rated. Right? They date from the World War II and were listed in blah 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 document published. You can Google that. You can download. Pretty much those are obsolete specifications, and you can see how old that document was. And it was published in 1962. The RG designation stands for radio guide. Now, what about those designations, the number sign that I put here? I listed 3, right? There should be one more, and I'll talk about that. The available for the commercial use are actually 4 types of cable: RG11, RG6, and RG59. What is it that those numbers mean here? So RG11, 6, and 59, for example. Treat them as a name. Whenever the engineers were designing a specific type of cable that would bear certain characteristics for mass production, they would have to register it as something. So when the engineers came up with a certain type of cable, they would go, okay, so we have a new cable that we're going to use for so-and-so, RG radio guide. Let's just take a look at the list. Did anybody register as so-and-so RG11? No, there's no 11. Okay, so let's name this one RG11. All right, so basically that was, it doesn't mean it has, 11 something or whatever. It's just a name. All right, that's how they would, those engineers would designate those numbers. So this is comparable thicknesses. Now that RG6 cable is the one that you probably see the most. So if you see a cable TV cable or the cable that's being brought to your house to serve your internet purposes, this is the one most likely you're going to see the thickness of that as RG6. Right? Then comparably thicker is the RG11, and then the comparably thinner, there will be RG59, and there's going to be one more that is RG58. All right. Now, why did I list these 3 beside each other? Because they have something that's called characteristic impedance that is the same for the 3 of them. I will talk about what characteristic impedance is, but in order for us to tackle what a characteristic impedance is, we're going to have to review, and this might help you with other subjects as well, what is impedance. And then based on knowing what impedance is, we're going to distinguish impedance and something that's called a characteristic impedance, and characteristic impedance mostly applies to the coaxial cable. Right? All right, so what did I write here? It's kind of when I was designing this presentation, I was trying to take you to this whole thing step by step, right? And as I said, this might help you with other subjects as well. See if I can. Yeah, that's going to be better. All right, so let's say consider a linear component such as resistor. What does it mean that the resistor would be a linear component? A linear component is, well, a linear quantity, as for example resistance or opposition to the electric current or waves. What means that it's linear, that means it's constant, it doesn't change. A resistor, when you have a resistor, whether you apply a DC current through that resistor, it is going to resist the current or oppose the current with a certain amount that is designed for. It could be 50 ohms, could be 75 ohms, could be 100 ohms, could be 600 ohms, whatever it is. That resistance of the resistor is not going to change. The ohmage or the resistor of that resistance of that resistor is going to be the same whether you apply DC current or whether you apply alternating current. And whether you raise the frequency of the alternating current or you lower down the frequency of the alternating current, that resistor, the resistance of the resistor is going to stay constant. So that means you can consider that as a linear device. Right? All right. Changes to the frequency of the source do not affect the resistance. Okay, so this is what I just said. The circuit is considered linear. The resistor will oppose the current with the same way, no matter the frequency. The current opposition equals to the resistance, and it is marked with the uppercase letter R. Okay. Now, we're going to look at something that's called a capacitor and a inductor or a coil. Now, just keep in mind, we are analyzing what impedance is, and the purpose of that is understanding what impedance is, to understand what the characteristic impedance is. Consider a nonlinear component such as capacitor. Now, when you apply capacitor into a circuit, if you apply the DC power to it, which would be the plus and minus on one side, and that thing doesn't change, the capacitor is going to charge up, so it's going to conduct for a little bit until the capacitor charges, right? So the electrons, the electrons are going to gather on one side of the capacitor, and the positive charges, if you can say that, are going to gather on the other side of the capacitor, and once the capacitor fills its capacitance ability of storing the electrical energy, the current is going to stop flowing. So to a capacitor, or sorry, to a DC signal or to DC power, the capacitor is going to act as an open circuit. What does it mean? An open circuit is basically there's no continuity there's no continuous path for the electrons to flow, for the current to flow. So if that's the case, then it's considered as an open circuit. Now, things are beginning to happen when you start alternating the current. If you alternate the current in the capacitor, you apply the circuit to two plates of the capacitor, it's going to charge up one way and it's going to stop the current. You switch the polarity, minus plus, plus minus. Well, then the electrons and the positive charges are going to find the opposite side, so they're going to flow back, and the whole thing is going to reverse. So that means there's current flow. If you keep changing the polarity, you're going to have a current flow in this whole circuit. So you're going to, if you do it very fast, you're going to have an alternating current through this whole circuit. So it just so happens that the bigger or the higher the frequency you're going to have, the more conductive the capacitor is going to seem. Of course, there's not going to be any charges flowing through the capacitor, but the whole circuit is going to have energy flowing through it, right? So with the capacitor, if you raise the frequency, the capacitor is going to be, the whole circuit is going to be more conductive. If you lower the frequency, the capacitor is going to seem more resistive to that. So now we're going to say that the capacitor, oh, hold on, I just gotta stop that. My computer wants to update. I'm just gonna say no, later, not now. Talking to my students now, right? Okay, so in this case, the capacitor is going to be always considered as a nonlinear device. Why is it considered nonlinear? Because if you raise the frequency, the capacitor poses less opposition. Higher the frequency, the less opposition from the capacitor. The lower the frequency, the more resistance or opposition from the capacitor. So in this case, you can say that the capacitor has a resistance, but the resistance is not constant. It depends on the frequency that you apply to it. Okay? So can we call it resistance? Well, technically you could call this a resistance. But to distinguish that from the linear type of resistance, we're just going to let the resistor keep its resistance, and we're going to call the resistance of a capacitor, we're going to call it a reactive resistance, right? Because the capacitor is going to react with its opposition to the amount of frequency that you apply to it. So it reacts. The higher the frequency, less opposition. Lower the frequency, which is going to be coming closer to DC, because if you lower the frequency less and less and less, 600 hertz, 500 hertz, 100 hertz, 50 hertz, maybe 1 hertz. And again, I'm just going to say, don't say 1 hertz, okay? It's not like a 3 hertz and 1 hertz. No, a hertz is a last name of a person who was studying long time ago resistance. Okay, so sorry, the frequency. All right, so hertz is always hertz. All right, 1 hertz, 2 hertz, and so on. All right, so when the frequency is going down with the hertz, it's going to go to 0 hertz, which basically is going to be constant plus and constant minus. Then the capacitor is going to resist more. Okay? No, guys, please. Yes, there is lab tomorrow for the B section. A section people had the same lab last week. This week, all the sections have the lab, but it's the B section people. B's, there we go. So what were we talking about? Okay, we're talking about the reactive resistance of capacitor. So you lower the frequency, capacitor is going to give you more resistance. You raise the frequency, the capacitor is going to give you less resistance. Capacitor's law of change. Right? Higher the frequency, the less resistance the capacitor is going to give you. It comes from the charging and discharging of the plates of the capacitor. So, because it's called it's called like reactive resistance, so we call it a reactance instead of resistance, because it's a non-linear resistance. The resistance of the capacitor depends on the frequency, so it's called a reactance. And in case of a capacitor, we're going to call it a capacitive reactance. Now let's take a look at the coil or inductor. Oh, the capacitive reactance it's a resistance, reactive resistance, reactance. We don't designate it with R. We're just going to go XC. Right? So that's the reactance of a capacitor. And the amount of capacitive reactance is equal to 1 over 2 pi fc, where f is the frequency, c is the capacitance of the capacitor. Now let's consider a nonlinear component such as an inductor. Right? To a pure DC source, an inductor acts as an extremely low resistor. So it's just the opposite of the capacitor. What's a conductor? What's an inductor? Inductor is basically a piece of wire wound in a coil. So if you connect a pure DC to it, plus and minus, it is going to act as a short. It's going to act as a closed circuit. If you connect a pure DC to an inductor, you're going to burn it out if you don't have any resistor there, because it's going to be just connecting a straight wire from plus to minus. Now, inductors, as opposed to the capacitors love change. Inductors are the opposite. They hate change. The more sudden the change is, the more kickback this inductor is going to give you. Right? If you raise the frequency, or if if you start raising the voltage applied to inductor, if you raise the voltage very slow, the inductor might not notice that, and it's going to still conduct, not going to give you any opposition. But if you raise the voltage extremely fast, the inductor is going to see the sudden change, and it's going to give you an opposite voltage on itself to oppose that change. And if you raise it fast and make it stay that way, then the inductor is going to see that, okay, there is no more changes, so I'm going to let go, I'm going to conduct. So what happens if you apply frequencies to a coil or inductor? Same thing. The inductor is going to resist more as opposed to the capacitor. If you apply lower frequencies, the inductor is going to resist less, which means it's going to conduct more. Right? So when it comes to inductor, in the opposition to a current flow, coil or inductor also has a reactance as opposed to resistance. And the reactance is called a inductive reactance, because it's a reactive resistance, because it depends on the frequency you apply to it. Remember, resistor, doesn't matter what frequency, it resists just the same, so it's a linear. These two are non-linear, because the resistance of those devices depends on the frequency that you apply. Higher frequency, capacitor is going to like, and the coil is going to hate. Right? The other way, lower the frequency, capacitor is going to not like it, but the coil is going to like it. Right? So that's how they both have reactances, capacitor and the inductor. They have reactances, but the capacitor is going to have capacitive reactance, and the inductor is going to have an inductive reactance. And the capacitive reactance is XC. Inductive reactance, we designate it as XL. XC, capacitive reactance, 1 over 2 pi Fc. And XL, there's no 1 over, it's just 2 pi FL, which L stands for inductance. Right? And as far as units, in all cases, the units are the ohms. Okay. So it's the Greek letter omega, or sometimes you can just say OHM, ohm. Right? So this is the difference between the way that these three devices conduct. All right? Now, let's keep going. The resistor, just to kind of put a stamp on that knowledge that we just got. The resistor is a linear component because its resistance value remains unchanged if the frequency increases or decreases. A capacitor is a nonlinear device because its resistance or value changes if the frequency changes. And here, there's a mistake I keep catching every year. An inductor is a nonlinear device because its resistance value changes as the frequency changes, right? Now, because of the resistance of a nonlinear component is affected by the frequency changes, we can say that the capacitor or inductor has reactive resistance. We call it a reactance. And here is the review of the last slide, right? Now, here is an interesting slide. You can do that as well. You have access to multisim. I just multisimmed a circuit, and I called up an oscilloscope on that, and I turned the whole thing on and applied the oscilloscope as if you were applying this oscilloscope in your lab. The only thing is that you can't measure current. Well, you can, but you have to do some gymnastics when it comes to measuring current, because normally oscilloscopes measure voltage, and you can display the voltage changes on the oscilloscope screen. If you haven't done that yet, you will. All right. So what did I connect here? I connected a power source. Here's a switch, and here's the thing. I'm analyzing this circuit here. Notice how is it that I'm analyzing this circuit? It is, see, this lecture here, this week's lecture, it talks about what we have to talk about when it comes to cabling and characteristics of the cables. But also we're analyzing circuits because, well, some things merge with other subjects. So this might help you also. This lecture here, if you really study this, it is going to help you with other subjects that you study within this course. Right? How is it that I'm analyzing the circuit? I'm analyzing the current path first. Same as if I were to build a circuit on the breadboard. If the circuit looks complicated, just take a step back a little bit and think about the current path. So what do we have? The current path, the current has to leave one terminal and come back on the other terminal, right? So how is it that we have the current loop going on here? The current leaves the positive terminal, goes through a switch, goes through a resistor, goes through a capacitor, and finds itself back on the common terminal. So here's a closed loop. Now, when we have established the current path, and sometimes you're going to have more than one current path, but that's a really good way to analyze the circuit or start building it so you don't get yourself tied into a knot. And then after you have analyzed the current path, then you're going to tackle the parallel devices such as voltmeters, oscilloscopes, or other things that are connected in parallel. Right? So what do we have in series? We have the current path established. Now we have connected an oscilloscope to basically across this resistor. So this will be the channel 1. Voltage across the resistor, and it will be current and the power supply. Now, I have also connected something that's called a current probe, because you can't measure directly. You can't measure a current through an oscilloscope. You can get something that is called a current probe, and in multisim, it's available for you, right? So if you haven't used multisim, try using it. And there are a bunch of YouTube tutorials on how to get yourself started, and you're going to in some subjects also, but get yourself a head start when using, because you're going to use that a lot. Okay? So what do we have here? We have a power supply. There you go, using digital last semester. Great. All right. So I bet you didn't know there's a current probe. Uh-huh. Well, now you do. What do we have here? We have a power supply voltage right here. There's a supply voltage, and notice I just applied a square signal to it, okay? Now, there is a current and a voltage going through a capacitor. And as a side note, I just played the frequencies, 100 hertz, duty cycle 50%, which means it's 50% on and 50% off as part of one cycle. Right? And I made a DC offset of 10 volts, so the frequency doesn't go below 0. So it just goes from 0 to 10 volts. So here's a 0 volts, 10 volts, 0 volts, 10 volts. Now let's take a look at what's happening at the capacitor. Here's the current. As soon as you, when there's no voltage applied, all three cycles, the voltage across the capacitor is at 0. The current, of course, is going to be 0, and because we have 0 volts applied. We're going to move to the point that the power supply suddenly goes up. Remember, when the capacitor is not charged, the electrons are going to rush through those conductors connected to the capacitor to charge it up until it fills the capacitor to its capacitance limit, and it's going to stop flowing. So when there's a maximum, so at the beginning, it is going to act like a short circuit, That's why I just put like a little current limiting resistor, just so the current doesn't flow as fast. Because if that happens, you can have problems. Right? So this purpose of this resistor is just to slow down the current, and it's called a current limiting resistor. So what happens? The current rushes up like crazy, and because the current is like the capacitor acts like a short circuit. Of course, if the component acts as a short circuit, there is no voltage between those terminals of that device because it acts like a short circuit. Right? So there's going to be no voltage because the current is at the maximum right there. It just rushes like crazy. Right? Now, as the capacitor fills itself up with the charges, the current is going to slow down until the capacitor fills up with the electrons or the charges. And the current is going to stop. And the capacitor is going to act like an open circuit because there's going to be no more current flowing through it. So of course, the voltage across the capacitor is going to be pretty much high. The highest it can get, providing the power supply. Right? So you can say that current leads in the capacitor and voltage follows. Right? In the capacitor, when the change is applied, first you get the current, then you get the voltage. Now, the cycle goes down. Of course, there's going to be current rush the other way, and the voltage is going to stay a little bit, but the voltage is going to start coming down because the current that would go other way is going to stop flowing. And when it goes on, it's just going to have, the cycle is going to be repeating. So that's basically what you're going to see. What I want you to remember is when the change is applied straight to the capacitor, there's a current that flows first. It makes sense. It starts charging, so it's going to be rush of current. and then the voltage follows. So in capacitor, current first, voltage follows. I'm going to take one more slide, almost done for today. Now, this is a magnified version of that. Right? Same thing. Let's look at the inductor. Instead of a capacitor here, we put an inductor, a coil. Now things are a little bit different. Let's look at the magnified version of what's happening on the inductor. Here's the supply voltage, and I just magnified the whole cycle here. Here's a sudden change. And remember when I said inductors do not like change. If you apply a sudden change to an inductor, it is going to resist that change. Right? It's going to act against you. The more sudden of that change is, the more aggressively the coil is going to react. So, looking at the graph here, current going through the inductor and the voltage across the inductor. So the change happens, nothing happens on the coil side. There's no current flowing. See, the red line is a current. And of course, the voltage is going to be high on it. Then, look, the change has been applied, and after the change has been made, things are going to stay the way they are. So coil is going to say, okay, no more change. All right, so I'm going to cooperate with you now. We can talk now because you're not changing. So the coil is going to start conducting. And once it starts conducting, of course, the voltage is going to drop again because coil is going to act as a short circuit. If it's a short circuit, there's no voltage across it. Right? So here is how we compare these two. In a capacitor, current goes first and voltage follows. In a coil, voltage goes first and then current follows. We're going to stop at this slide right now because I think it's quite enough for you to absorb. You know what? I'm going to post this video as well, aside from the other ones, so you can decide which ones to watch and so on. Right? In certain subjects, you're going to study this phenomenon. Right? Now, if you look at this, in a capacitor, first, there is a current and then the voltage goes down, happens. In the coil, first there's voltage and current follows. That we're going to later on, next time we see each other, which is going to be the next section. I'm going to repeat this class tomorrow, I think it is. We're going to repeat this class tomorrow, which is the same thing. And then we're going to go again, sections 1, 3, and 5, and sections 2, 4, and 6. We're going to put that against the reactances. And I'm going to leave you with one more thought here. One more thought I'm going to leave you with. Let me just gather my own thoughts here. Because if the voltage goes high, this way, that is going to cause the reactance go that way. Right? If the voltage goes that way, the reactance goes that way because voltage happens across a resistance. Voltage will not happen across a short circuit. And the voltage, basically the quantity of the voltage is in opposition to the quantity of resistance. The higher the resistance you get, the higher voltage you get, but they oppose each other. So voltage goes this way, the reactance goes that way. voltage goes that way, the reactance goes that way. So I'm going to just kind of remember this, because we're going to analyze that further down the road when we see each other next time. And there's a question here. Could you recommend a decent quality RCA switch box? Switch box as to for a video. You know what? Send me an email. I'm pretty sure you have something specific in mind. You're talking about the video and audio, RCA jacks, RCA composite video, separate video, audio left and right, RCA jacks. Send me an email and I'll talk to you. Okay, we'll see what you're challenged with. Okay, and hopefully I'll be able to recommend something. Okay, so this is pretty much it for today, and we will continue with the further slides next time we see each other. All right, any questions about what we have talked about? All right, if not, send me an email and we will tackle this next time we see each other. Have a nice day. Thank you, and drive safe. The roads are pretty bad today, so slow down. Okay, bye.